Hello, we are Group 6 from the Georgia Tech 4793 Composites Manufacturing course. Today, we will be presenting on the design and manufacture of advanced composite tennis rackets. My name is Andrew Crone. Joining me is Abhishek Kasturi, Anusha Raghuram, and David Sweetchang.
Amateur and professional players from all ages use tennis rackets to practice the sport all over the world. Only in the US, there are around 18 million tennis players. Tennis has progressed from a game played with hands in 1100 BC to the modern game it is today with advanced composite rackets. Wooden rackets, first introduced in the 1800s, were fairly cheap in price and used materials like maple wood and glue. The equipment used was an oven to cure the glue. With the improvement of manufacturing, metal rackets began appearing in the market in the 1960s. They were moderately priced and were made of aluminum or steel, and they used a die and an oven, as seen in this slide. Nowadays, composite rackets are standard, and they can be quite pricey. The materials they use include Kevlar, boron, and carbon fibers, as well as graphite and resin. They also need a mold and an oven, as seen in this slide. The performance requirements of tennis rackets are outlined in this slide. Tennis rackets are designed to be very robust at different environmental conditions and have an expected lifetime of between 2 and 6 years depending on frequency of use. Tennis rackets are considered engineering composites.
There are a few materials that are used to make a tennis racket frame in the market, including carbon and graphite, aluminum, and boron. The transition to carbon fiber frames from wood and aluminum was described earlier, and the switch was predominantly due to the unique properties associated with carbon fiber and graphite frames: lightweight, high stiffness and strength, high stability, along with high abrasion and wear resistance. The most popular material is graphite, which is a lightweight material derived from carbon. Racket frames can be made of 100% graphite or a composite of graphite and other materials such as Kevlar or boron. Pure graphite frames tend to have a stiffer feel, making them more suitable for players who hit with power. Composite graphite frames tend to be more flexible and transmit fewer vibrations, making them ideal for beginners. Compared to all other current commercially available reinforcing fibers, carbon fibers have the highest tensile strength to weight ratio, along with having the highest tensile modulus to weight ratio. A disadvantage is that they do have high costs. The next figure demonstrates the relationship between various fiber reinforced composites in terms of their tensile modulus and tensile strength. To reinforce what was said on the previous slide, carbon fibers are selected in the sporting industry due to their high strength and high modulus. Compared to thermoplastic polymers, thermoset polymers are essentially used for tennis racket manufacturing due to the higher performance criteria associated with thermoset polymers like epoxies. The table here demonstrates how thermosets like epoxies and polyesters have better mechanical properties than thermoplastics. They tend to have higher damping, a lower coefficient of thermal expansion, higher flexural strength and modulus, and lower density, all of which are desired for tennis racket manufacturing.
Modern tennis rackets are a lot wider and thus provide greater power and a larger sweet spot. The locations of these sweet spots are shown in the picture on the right. And the only drawback of these modern rackets are that they're harder to control because of the pronounced trampoline effect. Trade-offs in weight and flexibility must be made when designing a tennis racket. Lighter rackets are more maneuverable and have faster swing, but require greater effort. On the other hand, heavier rackets offer higher power for less effort and are harder to control. Some trade-offs must also be made in terms of flexibility of the frame. More flexible bases offer greater absorption and shooting precision, whereas stiffer frames offer higher power and better vibrational distribution.
Most advanced tennis rackets start from a base of carbon fiber prepreg sheets. These sheets are cut into predetermined lengths and wrapped around an inflatable bladder to form a tube. The direction of the wrap determines the racket's strength and flexibility. Additional layers of prepreg or other materials are added where needed. The wrap tube is placed in a racket-shaped mold to cure at moderate temperature and pressures. During curing, the bladder is inflated with air to add additional pressure from the inside. After cooling, the frame is removed from the mold and excess resin is trimmed. Painting takes place after this step. Only after painting takes place is the frame drilled for the string holes. Then, the
important parameters that are tested for after the tennis racket is manufactured include flexibility, tensile and compression modes, tensile strength, knot strength, durability, impact strength, and fatigue. Racket flexibility is measured in terms of a stiffness index, where a load is applied to a frame and the frame's response is assigned a flex value based on its deflection. A higher flex indicates a stiffer frame. The Lloyd LRX test is used to test the tensile and compression modes of the frame. The LS1 single column materials testing machine, along with the Nexigen Plus material test and data analysis software, is used to measure tensile strength, elongation of break, knot strength, and elongation percentage at given loads. Elongation is measured by using a 45 kilogram force to replicate the ball hitting the strings, whereas knot strength is tested to ensure that it is high enough. If it isn't too high, the strings can break.
It costs around $30 per racket to produce an advanced carbon fiber tennis racket, which typically retails between $50 and $200. These are expensive, relatively low margin products, and most of the profit comes from post-sale purchases such as restringing or additional tape. This concludes our presentation on the design and manufacture of advanced composite tennis rackets. Thank you for your time, and we hope you enjoyed this presentation.